Got it. Let's open the current slide. Okay. Before we get going on that, let me make these last couple of announcements. I wanted to have these here since so few people are in class. I hope you know by now, student course evaluations are open. Has anyone done them yet? Not yet? Okay, please do them. You don't have to do them. You can wait until finals if you want to. But please do them. Don't forget. I know when I was a student, in the finals week, I almost shut the brain down. It was not ready to think of anything else. So please don't do that before you do your student course evaluation. Then after that, you can shut it down. That's fine. But be sure you do it. If there's a likelihood you're likely to forget, go on and do them now. It's whenever you choose those, please do them. All right, another thing is let's just take a quick review of what's going to happen next. We're going to continue in 3.1 and hopefully get to 3.2 today. And then Thursday we'll continue in Chapter 3 as far as we can get. And that means that next Tuesday is when the exam is scheduled. It will be a two-part exam. The first part will be whatever we've covered in Chapter 3, and the second part will be the comprehensive final, which will be, both of them will be very short tests, probably 10 questions or fewer, and fairly, I think, easy for you to do in an hour and 50 minutes. You have an hour and 50 minutes for the final as opposed to an hour and 15 minutes of a regular test. So, and then you have as long as you need anyway, because you can continue. I have a class right after yours, but their final is scheduled for the other day, Thursday, not Tuesday. So I can stay here as long as you need me to. I don't have anything coming up at 11. I do have a 1 o'clock class, and their final will be scheduled. No, that's actually a mini-term class. It's 1:15. So I'm free until 1:15, so you can work as long as you want. I think you'll be able to finish both of them well within that. All right, any questions on anything? Math, scheduling, anything? All right, good deal. Okay, where we left off last time was in Chapter 3, Exponential and Logarithmic Functions, 3.1, Exponential Functions and their Graphs. We've introduced you to exponential functions. Now we do the graphs of exponential functions. This is on page 201. If there's no questions, we'll proceed. Here's example 2. On the same coordinate plane, sketch the graph of each function. All right. So what we'll do is set up get my pen darkened, and set up a probably the best of any. Okay, and Justin's here. Got enough for a basketball team now. Okay. So, there's our coordinate plane, and I'll tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Negative 1, 2, 3, 4, 5. Negative 1, 2 maybe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, let's plot f of x equal 2 to the x. How do we go about plotting a graph of a function? What's your technique? Preferred way? How do you do it? Been doing it all term. How do you do it? Second? Okay. You certainly can. And which intercept would you like to do? The x-intercept. That's where y is equal to 0. So you set f of x equals 0. That's your y. And when is 2 to the x ever 0? X is 1, that's 2 to the 1 is 2. It's not. It's never, okay? So x-intercept doesn't get you anywhere. It doesn't have one, which sort of indicates probably x-axis is going to wind up being a horizontal asymptote. Guess right now, but I think it's going to be right. How about the y-intercept? How do you get that? Say x equals 0, and what happens when you put x equals 0? 2 to the 0 is 1. So when x is 0, f of x is 1. So we got our one and only intercept. Okay? What would you do next? Okay? Okay, and like I said, we probably are going to get a horizontal asymptote, but that technique works for rational functions, where you can do ratio of leading terms. Okay, and also anywhere where x is not defined, well, x is defined everywhere in an exponential function. So no vertical asymptotes, and we don't have a ratio to do, though we suspect that the x-axis is going to wind up being, in other words, y is equal to 1, y is equal to 0, might be our horizontal asymptote. So, okay, I see what you're doing. You're using the techniques we did for rational functions. This is just any old function, not a rational function. How do you set up and graph any old function? Start plugging in numbers. And we did 1. 0 gave you 2. Give me another x. 2. And 2 raised to the second power is 4. So that would be 1, 2, 3, 4. Somewhere about there. 1. X is 1. What's your y? 2. Okay. Next. 3. X is 3. What's your y? 8. 1, 2, 3, 4, 5, 6, 7, 8. That would be somewhere right about there. Next one's going to be off scale. I almost guarantee it. Okay. So let's go the other way. X equal -1. What is your y? Let's do that one. F of -1 is equal to 2 to the -1. Everybody agree? So that would be 1 over 2 to the 1. That's 1/2. You're absolutely right. Next. -2, what would that give you? 1/4. 1/8. 1/16, 1/32. Getting awfully close to 0, but never is going to get there. So sure enough, that was a horizontal asymptote this way, and it just keeps on climbing. No vertical asymptote. You can keep adding x's, but as you do, the y's skyrocket. They have values. There's your graph of f of x equal 2 to the x. Okay, let's do g of x. Let's do it in a different color. You pick me a different color. Second? Green for g. I like it. Okay. So, give me an x. 1. And what is your y then? 4. Okay. Somewhere right about there. Make your dot big enough, you're bound to hit it. Okay. 2 would be 16, already off scale somewhere way up there. So let's go back. Say again? 1.5. Okay, you have to use a calculator and give me that one. Okay. All right. Let's go back the other way. -1, what would that give you? 1 over 4, so that would be 1/4. Would be 1/16, way down there, okay? I can't get the pen to mark. There it is. Next one. -3 would be 1/64. And yeah, they keep getting smaller. So this approaches 0. You left off 1, though. One of the easy ones. 0. And what do you get when you put 0 in? Not Amber. She's present. Okay. What do you get? 1. Huh. So here this takes off and goes up really, really fast. And it comes down pretty fast, but still approaches 0. But it doesn't wiggle like that. It's just my drawing that does. There's what we got. Same coordinate plane, sketch the graph of each function. So as x increases, boy, does that g of x go up even faster than f of x did. And f of x went up awfully fast. Everything seems to go through the point 0, 1. Of course it does. For exponential functions, they all go through 0, 1. Okay, because for x is 0, your y is always 1. And then the one with the large base flattens out more quickly, than the smaller base always exceeds it by a little bit. Okay? Pretty ugly graph, but you get the general idea? Any questions on it? I kept thinking someone would say they like to do T-tables. That's how generally most people were taught to graph, and you could do that. They do horizontal tables in the text, or you can just plug and chug like you did. And any of those are perfectly fine. There is a checkpoint there. Highly recommend you go home and work that, or the library or classroom or somewhere where you have a chance. Do that while it's still fresh on the mind. So what I'm going to do, if there are any no questions on this, then I'm going to erase this ink and we'll watch how they did it. Well, they did their horizontal table, and they did the 2 to the x, when x is minus 3, that'd be 1 over 8, minus 2, 1 over 4, minus 1, 1 half. We had all those points 0, 1, 1, 2, and 2, 4. We actually did 3, 8, and got that on the graph. When you did 4, x to the minus 3 is 1 over 64, awfully close to 0. X to the minus 2, 4 to the minus 2, 1 over 16, minus 1, 1 over 4, 0 is 1 again, 1 is 4, 2, 16, 3 would have been 64. Way off scale. Well, 16 was off our scale. And, all right. Let me find you. Which one? Huh? Oh, both of you came out. I didn't see but one. Okay, sorry about that. I only saw the first come in. Sorry about that. I was looking on the graph. So got you both. Okay, got it. Okay. Now, since a few people have come in since I made the announcements earlier, I probably have to make more as others come in, but so I won't forget it. Please, if you haven't done them already, do the student course evaluations. They are open. You can do those, and they always ask for a few things besides just your courses, things like registration or library or something like that. So, please do those, please. Okay. Now you can wait till later in the term if you want to, but we just don't have much term left. I guess everybody knows today is the beginning of the last week of class. We have class today and class Thursday. That means your research papers are due this week. Today, tomorrow, or Thursday, okay? After Thursday, they're going to start losing points. So please get them in today, tomorrow, or Thursday, okay? Also, on Thursday, I didn't make this announcement earlier. I meant to. I'm glad I got back to this. Thursday morning, beginning of class, I'll be returning all quizzes, all tests to you, okay? Which means if you haven't turned in a quiz yet, get it into me today, tomorrow, or by the beginning of class on Thursday. I won't be able to return those to you because I won't have time to grade them. If you get them to me today or tomorrow, I will hopefully have a chance to grade them and get them back to you on Thursday morning. That also means if you put do not grade on a test, I've done a partial and you can see what your partial score is. Most of those are not very pretty, so if you are going to finish a test, you need to finish it today, tomorrow, before Thursday morning. So that's basically today or tomorrow. Not going to have but 15 minutes before, I usually get here between 7:30 and 7:45, so you're going to have very little time to work on the Thursday morning before class. So if you haven't turned in a quiz, get it to me today or tomorrow, or first thing Thursday. If you haven't finished the test, finish that today or tomorrow, okay? I'll go over my office hours again. Today I have the only major chunk of office hours I have 10:45 to 1:15, okay? That's the only one. Now, at 1:15 I start a physical science class that goes until 3:45 of class, and then we have a lab from 3:45 to 5:45. I'm guessing, I don't know this for sure, I'm guessing the lab won't take the full 2 hours. So sometime probably around 5 o'clock, we will be able to, we'll be probably back in the office or somewhere close to the office, close to being back in the office. So you can catch me then if you choose, okay? And otherwise, anything you want to turn in, slide under my door. So let me go over that again. Please do the student course evaluations. If you haven't already, get them done sometime soon. You can wait until, finals week or after finals week, but not long after finals week. They shut it off somewhere toward the end of finals week. So please do the student course evaluations. If you're likely to forget when finals are over, do them before finals are over. Okay. Number 2, I will be returning all quizzes, all tests that have been turned in so far to you next class, beginning of class on Thursday. So that means if you haven't turned in a quiz, get it to me today, tomorrow, or by Thursday morning. We'll start this over. Okay, Ashlyn's here. Okay. Again, student course evaluations are open. Please get them done. Okay? Secondly, your research papers are due today, tomorrow, or Thursday. After Thursday, I'll still accept them, but they start losing points for being late. Last day of class is when they were drop dead dates, so that's when you get full credit Thursday. After Thursday, I'll accept them, but you'll be losing points for being late. Okay. First thing Thursday, when we come to class, that's day after tomorrow, last day of class, I'll return all your quizzes, all your tests. Can't return your research papers because they periodically request samples of student writing, so I have to hang on to those. But your quizzes and tests I'll return to you. So if you haven't finished, if you put not finished, do not grade, something like that, I've graded everything you've done so far. I think I've got one left to grade. But the partial scores for those people who aren't finished are not very pretty. I don't think you want that as your final score, but if you don't haven't done anything by Thursday morning, that goes down as your final score. So please get with me today or tomorrow and complete any tests that you may be short or missing. All right. And then next Tuesday, 1 week from today, is the final exam. Now, the final exam will exist in 2 parts. The first part will be a test on Chapter 3, what we covered today. We started it Thursday, what we covered today, and this coming Thursday, okay? I guess it was Tuesday we started it, okay? So that will be the first part. Very short test, fairly simple, just get it done. And then your comprehensive part will be no more than 10 questions, 1 sheet, and it'll cover some questions, probably 4 questions from Chapter 1. Chapter 1, 4 questions from Chapter 2, and maybe 2 questions from Chapter 3. Okay? So that will be your final exam. Okay? The comprehensive part. So it'll be 2 short tests, 1 Chapter 3 test and 1 comprehensive test. Okay? Both tests you can have formula and equation sheet, anything you want to bring in. Okay? Any questions? All right, let's continue. This was example 2, top of page 201 in chapter 3, which is exponential and logarithmic functions, 3.1 exponential functions and the graphs. And we were just doing example 2. These are the graphs of 2 to the x and 4 to the x. Notice 2 to the x, I wish they had done different colors, rises more slowly than 4 to the x, but still rises and goes up really, really fast. That's characteristic of exponential functions. Everything goes through 0, 1, because you raise anything to the 0th power, it's always going to be 1. Okay? And then on the left-hand side, negatives, this flips the base raised to whatever power to the denominator, so these are your fractional forms. And here, the function that goes up so fast on the right goes down fast on the left and approaches 0 much more quickly. The one that goes up a little more slowly on the right comes down more slowly, and actually the 2 to the x is always greater than 4 to the x, less than 0, and 4 to the x is always greater than 2 to the x, greater than 0, at 0 they cross. Okay? So that's how an exponential function looks. Any questions? Now remember what distinguishes an exponential function from a polynomial function? Okay. On a polynomial function, your variable is the base. Numbers are your exponents. In fact, integers are your exponents. In fact, positive integers are your exponents. On exponential functions, numbers are the base, variables are the exponent. Okay? So, now, that was example 2. Note that both graphs are increasing, always increasing. Moreover, the graph of g of x equal 4 to the x is increasing more rapidly than the graph of 2 to the x, especially to the right, but even to the left is increasing more rapidly. It's hard to tell, they're both so flat here, but it is increasing more rapidly, even for negative numbers. Okay? So the larger the base, the more rapid the rate of increase. Now these are for positive bases. Okay? We only have positive bases. I mean positive, well, never mind. Okay. You'll see next. I think they skipped. Yeah. Yeah, they skip example 3, so let's go back and we'll do example 3. We'll do it here. In example 3, we have 2 different functions. Let me get rid of my green, go back to my dark. And here we have, rather than little f of x, and they just chose this, capital F of x, is equal to same base, but now it's negative x, okay? And then the capital G of x, they just chose to name it this way, capital G of x, and this is no fixed way, that's just the way they chose to do this one. That's equal 4 to the negative x, okay? All right, we're going to do the same type thing that we did before. I'll draw in the graph. And you might note, I've moved my vertical axis here. What's he up to here? 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 1, positive 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not very even on my vertical axis, but I think you can live with it. How would you go about graphing these two? Let's do 2 to the minus x. Give me a number. 0. And what would that be? 1. Because 2 to the 0th is 1. Anything to the 0th is 1, except 0 to the 0th is not defined. Okay? Next. If you plug in a 1, what do you get? 1/2. Next would be a 1/4. Next would be a 1/8. Next, 4 would be a 1/16. 1/32, 1/64. I can't distinguish those. Let's go to the other side. Would be a what? 2. -4. -3 would be 8. That's 5, 6, 7, 8. Somewhere right around there. And -4 would be 16, which is off scale. So here is your graph here. Now basically, that's exactly the same shape that we had before, but because you negated the x, you reflected it across the y-axis. Before it went like this, like that. Now just reflect that across here, and you got it coming down here. Okay? Green for your G. Okay? All right. Give me an X. 0 will give you 1, same as before. Will give you 1/4. 2 will give you, no, like 1/16, isn't it? 1/16. 1/64. You know, ew, tiny, tiny numbers. Okay? How about going to the left? -1 would give you 4. I think that's right there. -2 would give you 16, already off scale. Okay? There we have your graph. Okay, not drawn very nicely. But you see this, again, reflected across the y-axis. It's very similar to what we had before, except this time to the left, it's going up very rapidly. The larger base goes up more rapidly than the other and goes down more rapidly. Okay, so the larger base is always greater on this side than this one, always less on this side than that. But if you look at it the other way, increasing numbers in x, both of these functions are decreasing always. The rate of decrease is greater for this one than it is for that. Okay, everything. And again, they get very big, very, very rapidly. But now with negative things. Now, notice a few more things about exponential functions. Notice I always drew my x-axis down here. Why? They're always positive and never negative. Okay? Everything always goes through 0, 1. Okay? And if the exponent is a negative variable, it's a decreasing function. If it's a positive variable, it's an increasing function. Okay? Those are two things to notice. Let's notice a few more. Okay? And that's what we did here. The following summarizes the basic characteristics of exponential functions. Y is equal to a to the x, and y is equal to a to the minus x. Now remember, again, a's are never negative, never 0, and never 1. Okay? So everything and anything else can be a base. Okay? If you think about it, 0 is a base, it's a flat line. I mean, it just doesn't do anything. Always 0. 1 is a base, flat line again, but always 1. Okay? So those two are not very interesting. You can't have a negative base because this x could take on things like a half, 1/2, and you can't take the square root of a negative number, or any even root of a negative number, so don't ever put a negative base in there. Okay? Your exponents can be negative, positive, doesn't matter. Okay? So with positive bases, always, not 1, positive bases other than 1, then this is what your graph looks like. Okay? Now, so the graph of a to the x, and let's just choose the a's greater than 1. Let's not even mess with the small ones. You could have between 0 and 1. We won't mess with that now. We'll do that on the next slide. Okay? Then, your domain, all real numbers. Range, greater than 0. Notice it's a parentheses in front of the 0 because 0 is not included in the range. It never equals 0, okay? But it goes to positive infinity and heads up there pretty quickly, okay? Y-intercept is always 0, 1. X-intercept doesn't. Never reaches 0. These are always increasing functions if your a is greater than 1. These will be increasing functions. And the x-axis is a horizontal asymptote, but it's only a sort of like a one-sided asymptote. It's what happens for large negative values as x, a to the x approaches 0 as x approaches negative infinity. Okay. It's always increasing function, blah, blah. It's a continuous function everywhere, okay? Continuous function. So that's when you have a base greater than 1 and a to the x. Not a to the negative x, but a to the x. That's the shape. Now, here's sort of a bizarre thing. Not yet, really. This is what we've already seen. If your a is raised to the negative x, and again, your a is greater than 1, like we had 2 and 4 before. What's your domain? All real numbers. Range? Everywhere greater than 0. Y-intercept? 0, 1, same as before. These three are identical. But the next one, decreasing function now. Again, the x is a horizontal asymptote, but on the other side, a to the minus x approaches 0 as x goes to positive infinity. And again, they're continuous, always continuous functions. Notice that the graph of an exponential function is always increasing or always decreasing, never has a change of direction. In other words, the relative minimum maximum. None, ever. Okay. Now, notice that was always with a's greater than 1. We'll come back to this later. As a result, the graphs pass the horizontal line test. They're always increasing or always decreasing. Pass the horizontal line test. Therefore, these are always one-to-one functions. Exponential functions are always one-to-one functions. Guess what? That happens if they're a one-to-one function. What's then also true. Or did we ever mess with the horizontal line test or one-to-one functions? When do we do that? When we're talking about inverses. Exponential function does have an inverse. Okay? Now, the other reason that we mentioned one-to-one properties here, they're not mentioning inverse yet. We'll get there. Because they're one-to-one, for all the a's greater than 0 is not equal to 1. Now, we haven't messed with the ones between 0 and 1 yet. We will. Okay? If you have an expression like this, any base, not negative, not 0, and not 1, okay? Any base raised to the same power, if you know those two quantities are equal, because they're one-to-one function, that means that x is equal to the y. It's got to be. That's the one-to-one property. And because all exponential functions are always one-to-one, you can use that now. You can't use it other places that you could have a variety of values, but here you can because these are one-to-one functions. Okay. Now, they're ultimately going to get to it. I wish they had done it now, but they aren't. So I'll hold on. Okay. They're jumping to the natural base e. We haven't done example 4. We haven't done example 5. So let's do those two first. Let's see if we can find some room to do them. Let's clear this. Okay. Let's see, I'm going to find a better place. We're going to do them here because this is the one-to-one property. Don't have much room, I'll erase a lot. So example 4 says, what if we have, let me go back to my dark thing, 9 is equal to 3 raised to the x plus 1 power. Okay? Now, right now we don't have any ways to solve that. Okay? We don't have those tools in our belt to solve an equation like that. Okay? You might have some ideas, but don't have them yet. Except for this. If we can get this equation to look like this, in other words, to come up with the same base, right? So here we know the base, right? 3. Can you write 9 as 3 to some power? What? 9 squared. Okay, so that will work. I mean 3 squared. Didn't we say? Okay. 3 squared is equal to 3 to the x plus 1. That's 9, right? 9 is 3 squared. Now we can use this property. What does it say has to be true? That 2 is equal to x plus 1, right? Which means subtract 1 from both sides and you have x equal 1. Yeah, we can solve that. We can solve it because we know this can be written as same base raised to some exponent. Okay? Now, they show you in the example here, but we haven't done anything like this, but it's still a legal move. Okay? What if we have the B part, 1/2 raised to the x power is equal to 8. Now, like I said, all the examples so far have been bases greater than 1. You can have bases between 0 and 1. Here we have 1. So we got to figure out, goodness gracious, how can we do this? How can we do this? Is there a number 1/2 raised to some base that would give you 8? -3, that's exactly right. So 1/2 to the x is equal to 1/2 to the -3. Now, check and see if that works. Okay. 1/2. Okay. I think, yeah, we can do this. This is the same, if you think about it, as 2 to the +3, right? 2 over 1 to the +3. And 2 to the 3rd is 8. Yeah. So that might be the way to back into it. So what does this give us from the 1-to-1 property? X equal -3. Perfect. Got it. Well done. Okay? Now, the next little thing they do, and I always was biting my tongue when I said it, what I was saying, exponential functions, remember I sort of said, always go through 0, 1. Well, you can translate exponential functions, all over the place. You can stretch them, you can do other things. So when we do have those translations, we may not go through 0, 1. Okay? I was talking about the basic one. So what we're going to do here in example 3, it says each of the following graphs is a transformation of the graph of f of x equal 3 to the x. Now this one, I think that we got to go back to this slide. Okay? So we're going to do f of x is equal to 3 to the x. Now you tell me how to graph that. Let me see before I do. Yeah, I'm going to need this here. We need the whole graph and nothing but the graph. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Positive 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. Okay. Tell me how to graph alpha of x equals 3 to the x. Give me some points. 0, 1, good one to start. Second, 1, 3, excellent. 2, 9, that's 2, 3, 4, 5, 6, 7, 8. Somewhere up there, okay? Okay? Negative 1, 1/3, 1/9, 1/27, 1/81. I can't get any closer than that, so it's a function that does like this. Okay, there's your alpha of x. Now, what color? Second? Green again? Okay, we're going to do our g of x. Okay, g of x is equal to 3 to the x plus 1. What you reckon is going to happen with that? Say again? It won't go through 0, 1. Got that one. But when this exponent is equal to 0, the value is still 1. What makes the exponent 0? X equals negative 1. So negative 1, 1 will be that one. Okay? So guess what has happened here? It's a horizontal shift to the left because that's a plus. Remember, anything you're doing to the x goes in the opposite direction. So that's 1 to the left, that's 1 to the left. Somewhere up there is 1 to the left up here. And then this is 1 to the left here. This is 1 to the left there, and on like this. So here, down here you can't tell much difference. But here we have you shift to the left. Everything shift to the left 1. Okay? H. You pick another color for H. Second? Second? Light blue. Okay, here will be our H. H of x is equal to 3 to the x minus 2. What? It's a vertical shift down 2. Exactly. From our original, go down 2. So, okay, it goes through there. This one goes down 2, so that would be here. This one up here will go down 2. It was 9, remember? Now it's going to be 7. 1, 2, 3, 4, 5, 6, 7. There it will be right there. Oh, there. Yeah, get out of there. Okay, somewhere there. I think. No, it's on this side. There, I had it right the first time. Okay, next. This will be, that was 1/3. It goes down to 1/3 above 2, negative 2. 1/9 above negative 2. So basically, I'm going to use my red here. We have our horizontal asymptote has shifted down to y is equal to negative 2. So our function is approaching negative 2 down here, and then it's going up like that. So it's a downshift of 2 down. All right? K of x. I need a different color. Say again? Purple. So here's our K of x. Are there any questions? Or is this making any sense? We did this before, so I was hoping it would sort of make sense. What happens to K of x? K of x is equal to negative 3 to the x. Whoa, what's happened here? What's that? I can't.
It wouldn't exist. It would not exist.
Okay, no. It's not negative 3 to the x. It's negative 3 to the x. You're negating your g. Your h. Your f. Negating f. So what does that do? You're negating the y values. It flips them across the x-axis. That's it, exactly. So your 0, 1 becomes 0, negative 1. Your 1, 3 becomes 1, negative 3. And your 2, 9 becomes, let's see, 3, 4, 5, 6, 7. Yeah, we don't have enough room there either. This 1/3 becomes negative 1/3. Oops, somewhere like that. And then 1/9, and 1/27, and 1/81, and on and on and on. So again, it's approaching a horizontal essence right there. There it goes. It's just a reflection of your basic graph across the x-axis because you're negating the y values. The x values stay the same, the y's get negated. Make sense? Reflection across the x-axis. And the last one, I need a color. Dark blue. Okay? J of x, okay, is equal to 3 to the negative x. Oh, we've already done that one, haven't we? What did it do? It flipped it across the y-axis, just like we did before. That goes there, this goes here, this one goes 1/3, 1/9, 1/22, yeah, like this. So this one's coming down like that. We didn't do it with 3, we did it with 2 and 4. And yeah, that reflects across the y-axis. The dark blue here, and the middle blue here, exactly your images across the x-axis, the y-axis. Does that make sense? So we can do all of our translations, our vertical translation, up or down, horizontal translation, right or left. We can do our reflections. We can do our across the x-axis and y-axis. Everything works pretty much like we did before. Okay? So, they have a checkpoint there, well worth your effort. Okay. Let's move on to what they've been trying to get to on the slides for a while, the natural base E. Why in the world would they say that? If I ask you what's the basis of our number system, what would you tell me? 10, okay? Because in adding and subtraction and multiplication and division and just everything, we got 10 fingers. I think that's where it came from, That's why we have base 10, okay? And that works for all of our arithmetic operations pretty nicely, okay? However, the natural base for all of nature doesn't seem to be 10, okay? It seems to be some weird, irrational number, E. And when I say all nature, when you get into calculus, and this is pre-calculus, that's what we're getting here. And there's some really incredible things about this natural base E, okay? Well, you won't hit them all now, but hopefully some of you will continue and do calculus, and when you do, you'll see E is your favorite function of all time because it's so easy. Okay. In many applications, the most convenient choice for a base is the totally irrational number. Now, this doesn't look like it's an irrational number, but believe me, it is. 2.7, 1828, 1828. It looks like you got a repeating section here. But if you have a big enough computer that you can carry far enough, after this, it's random numbers from then on. These just happen to be repeating that twice here. That's not a section that repeats every time. I don't know if any of your calculators will do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. I doubt if they will. Okay, but you won't be able to see it. But if you had a computer that will print out more, you'll see that after this, they're all random. This just is a fluke that they're the same right in there. In fact, my guess this is a roundup here, so it probably isn't even close to that. Okay, but it's close. Usually what I use, 2.7, and sometimes they even say 3. Okay, but that's just an approximation. That number is the natural base of our system. So the function f of x equals e to the x. So we never write this number down, we write the number e. Okay, e to the x is called the natural exponential function. Okay, now like all exponential functions, it goes through 0, 1. Now if you did 2 to the x, that would be a little bit below this and above it here. If you did 3 to the x, it would be just a little bit above that. So it's right in there. It's just a number in between 2 and 3. Okay? And it just fits that, has the same pattern, everything's the same. Your calculators, most calculators will have an E key on it, E to the X. Depends on your calculator, you know, the syntax you use. You either hit the button first, opens a parentheses, put the number in, like -2 or 7 or whatever you want to do, and then do equal. The old calculators, like mine, I have to enter the number first, like -2, then press the thing and it gives me the number. Just depends on your calculator. You need to know your calculator. But that's how you do your natural base exponential function. Okay, E function. Okay. Says be sure you see that for the exponential function e to the x, e is a constant, whereas x is the variable. Okay. Just like all the others, it's an irrational constant, not an easy one to write down. So we use the number e. So example 6 has you do this. So pull out your calculators. And folks, please bring your own calculator to the test. The only reason I say that, the test is not a good time to learn a new calculator, okay? It's a good idea to be familiar with your calculator so you know how it works. I'll be glad to supply you a calculator because I only have like 1 or 2, only one that'll do this. But I'll explain to you how to do it. But that's not the best time to do it. So since you are going to have some of these to do, bring a calculator that you know how to do. So I want you to use the calculator to evaluate the function f of x equal e to the x at each of the following. X equal -2. Now, if any of you don't know how to do it on your calculator, get me to you and I'll show you. Anyone not know how to do it on your calculator? Okay. You got it? What do you get? E to the -2. Wait, let me get my pen back. Say again. 0.131335, blah, 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 blah. Okay. Irrational number, by the way. Now, does that make sense? Remember, I usually use 3, okay? 3 to the -2 would be 1 over 9. 1 over 9 would be 0.11111. So, yeah, this looks pretty reasonable. It's not quite 3, 2.7, so it's going to be something, yeah, that's a reasonable number. Okay? How about x equal -1? What would you get? 3, 2, 3, 6, 7, blah, 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 blah. Okay. That again seems reasonable because 3 to the -1 would be 1/3, which would be 0.33333. This isn't quite 3. This is 2.7 something another, so 0.36. Blah, blah, blah. That makes sense. Okay, what if x equal 0.25? What would that be? 0.778, blah, 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 blah. Okay, all these are irrational numbers, by the way. Okay, now let's see if that makes sense. Let's imagine 16. It's nowhere close to 16. But 16 to the 0.25 would be the 4th root of 16, right? And the 4th root of 16 would be 2. Well, this isn't nearly up to 16, So this is something that's not a very good example. 1, of course, would be, the fourth root of 1 would be 1. You just have to take them over. Okay. Better way to think of it. I don't think this is true, is it? That's not right, is it? That I don't think it can be right. Say again? Ah, 1 point what? A little louder. 284. Blah, 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 blah. Yeah. I knew, because when x is 0, you're at 1, and you're increasing past it. It has to be something greater than that. Yeah. So, yeah, that makes sense. Not a lot greater, because x to the 1 would be 2.7. X to the 0 is 1, so it has to be between 1 and 2.7. So, yeah, looks good. How about x to the negative 0.3? X equals, say again? 0.741. Dot, 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 dot. Okay. Again, an irrational number. It keeps going on and on and on. But this time, we're not as small as this. Okay. At 0, it's 1. At negative 1, it's 0.367. So somewhere in between that is 0.7. Yeah, that makes sense there. So again, anytime you have a positive number, it's something greater than 1. A negative number is something between 0 and 1, going down from there. So it makes sense, right? Did everyone manage to get your calculator to agree with these? Any questions? I'll be glad to try to help you see how to use your calculator. Now, if you have a simple cheapie, it's not going to do exponentials at all. But if you have a scientific calculator or better, it will work. Any questions? Let me help you now before you get stuck on the test. Anyone can't get these? You all got them. Still working at it? Everybody okay? All right. Then let's clear this out of the way, and let's see how they did it. Okay? Now, they're talking about a specific kind of calculator. Okay? Not my old scientific calculator. This is what I call a display calculator. Maybe the newer ones. That first one, when f is equal to minus 2, your e to the minus 2. So find your e key. Now, this key is not the subtraction key. There is a minus key over there with plus, minus, and multiplication and division. That's not the one you use. You use the one that's in parentheses. That's the negation key, not the subtraction key. So the e key, the negation key, and then 2, and then enter. Now, do any of you have a calculator that doesn't work? If you do, I think I can find that for you. Like my old scientific calculator, what I would have to do was press a 2 first, and then I have a key on mine that says plus minus. That changes the sign. So I press that next, it makes it a negative 2, and then I press the e to the x key, and then it erases that to the negative 2. So some calculators use a different syntax, but most of the newer calculators will use something like this. And sure enough, we got 0.135, and that's what we figured it was. Right. Any questions? Okay. Know your calculator. Okay. Sometimes your calculator gives you phone calls, don't they? Okay. Now, f of 1, x equals negative 1, e to the minus 1. Same thing. E to the x, negation key, this time 1. Enter, you get 0.367. Just like y'all got before. Everybody see how to do it? Okay. Any questions? Okay. When x equals 0.25, e to the 0.25, you know that's got to be between 1 and 2.7. So you know that mentally. So you e to the x. Now you don't need a negation key because it's positive number, 0.25, and they're between 1 and 2.7. Good deal. But then you go back to negative again, negative 0.3. Now this is between 0 and negative 1. At 0, you're at 1, and at negative 1, you're at 0.36. So you know you got to be something between 0.36 and 1. So let's see what we get. E to the negation key, 0.3, enter 0.74. Yeah, that makes sense. On the way to 1, greater than 0.36. Yeah, we'll buy that. Make sense? That's your exponential function and how to do it on calculators. When you get home or get a break or sometime soon, try to do the checkpoint. Do a few more of those. Okay. Before we get to applications, there is example 7. Okay, let's do example 7 here. All right. Sketch the graph of each natural exponential function. Okay? All right. So I'm going to do my graph here. Okay. Okay, something like that. Now they didn't do the base E. I could do that, but let's just do what they ask us to. We don't have a lot of time. F of x is equal to 2e to the 0.24x. Okay? How would you do this? Plug some numbers in. Give me a number for x. Okay? And what would you get? This part would be 1, but then you're multiplying it by 2. So this is a vertical stretch. We didn't do those earlier, but that's a vertical stretch. That gives you 2. I mean, put it in your calculator and see.
So when you have a decimal in your exponent, that's...
Okay, that has nothing to do with it. You put a 0 here, that's still 0. E to the 0 is 1. Multiply it by 2, that's what makes it 2. Okay. So you're at 0, 2. And that was the other reason I cringed and bit my tongue when I said it always goes through 0, 1. Your basic exponential functions do. When you do translations or stretches or shrinks, yeah, it's going to change it. Okay, give me another x. You're going to need your calculators, folks. Give me another x. That one I can do. The x equals 0. But you give me another one. Okay. So, 2 times e to the 0.24. And what do you get? 1.27? Yeah, that's right. 1.27. Okay? Something about there. Okay? Give me another one. Second? Wait. I'm not sure about that. Wait a minute. No, this is a positive number. That can't be right, the one you just gave me. I hesitated and then went along with it, but no, I don't think that's true. Because you see, if this exponent is larger, 1 is 0, it's now 0.24, this has to be greater than 1, and 2 times something greater than 1 is going to be something greater than 2. I think. Can you not get it to work? Oh, I see. Okay. I don't know what syntax your phone uses. What you might want to do is, you can do an exponential function on your phone? Okay, so do a e to the 0.24 and multiply that by 2. That sounds better. Say again. 2.54, somewhere about there. This is going the right direction. How about 2? And again, I would do it in my head. E to the 0.48 multiplied by 2. Now, if you got a scientific calculator, you don't have to do it these steps. You can do it. I don't know how phones do their syntax, so I can't address that. What's that? 3.23. That'd be somewhere about there. Okay? Let's try 3. 3 times 0.24 would be 0.72. E to the 0.72, and multiply that by 2. 4.1, somewhere right about there. Okay? X equal 4. That'd be 96.96. E to the 0.96, multiply that by 2. 5.2, somewhere right around there. Okay? That was 4. 5 would be 1.2, I think it is, yeah, wouldn't it? Yeah. Yeah. E to the 1.2 times 2. 6.6, that's somewhere, let's see, 1, 2, 3, 4, 6, somewhere up here. My graphing skills are not great. Okay, how about 6? 0.24 times 6, e to that number, and then double it. 8.4, 1, 2, 3, 4, 5, 6, 7, 8.4, somewhere up here. Like there. Let's see, can we get one more in? That was what, 6? 2.24 times 7, e to that number, and multiply by 2. Yeah, that's off scale. Good. Okay, how about negative 1? E to the negative 0.24, and multiply that by 2. 1.57, okay. E to the negative 0.48 times 2. 2nd? 1.2, that looks reasonable. Okay. E to the negative point, what was that, 72? And multiply it by 2. 0.97, somewhere here. You get the general idea, don't you? Okay. Now, because this number is a pretty small number, this is a very gradual rise, but it still is exponential. It's going to keep going and going and going. Okay? The next one, and I don't think we'll have time for it, is g of x. You want to do that next time? I don't think we're going to have time. We're already out of time now. So, let me, I don't have an eraser worth anything. I do too. Okay. We'll start with example 7b. Someone walked off with my last pen. And okay, let me give you some homework exercises. We got decent progress on this. Do any of the odds 7 through 11. Do either 13 or 15 or both. In fact, I would do 13 through 16. The answers for 13 and 15 are in the back. Do any of the odds 17 to 21. Do either 23 or 25 or both. Either 27 or 29 or both. And then try to do 31 or 33 or both. Okay? 35 or 37 or both. Any of the odds 39 to 43. Any of the odds 45 to 49. And we'll stop there and pick up there next time. Okay? Good deal. All right. Next time, remember, okay, I don't think anyone else new came in. Anytime between now and the end of the term, please do your student course evaluation. Please do those. Okay, before next class, finish your research papers and turn them in by the next class. Come in and make up any tests that you haven't done. Turn in any quizzes you haven't turned in, and I'll be returning everything that's been turned in by Wednesday evening. I'll return it to you Thursday morning, okay? Except for research papers, I can't do that, okay? Any questions? I'll be returning all your papers to you except research papers Thursday morning, first thing. That way you have a chance to ask me questions on anything you may have missed. Tomorrow? Yeah. My office hours are, the biggest chunk of offices are 3:15 to 5:15. Okay, I have little bits here and there otherwise, but that's the biggest chunk. But you can come in anytime, either before class or between classes, and you can get it and work on stuff if you want to do that. So, okay.
Oh, can we finish it?
What's that? Oh, yeah, you want to work on yours. Okay. Okay. Test 2. I do. And this is just 2 classes. There's Amber Reese right there. I gave you back your formula equation sheets. What's that? What's that? Okay. Ryan King, there you are right there. Okay. Y'all can go next person.
I'm coming at 10:45.
10:45 today? Okay, fantastic. Okay. I'll be there Friday, so that's late. Yeah, I've got classes today here until 5:45, and tomorrow I have classes from 8 o'clock until 3:15. 3:15 to 5:40 to 5:15. Yeah, you can come back to that. Okay? Okay, you started it, didn't you? Yeah, okay, I remember. There you are. Okay, see, I got to return everything Thursday morning. I'll be here from 10:45 to 11:15. I mean 1:15 today. And even after 1:15, you can still work on the test. I'll just be in class. And then I'll probably be free sometime around 5-ish or so, if that's better. Okay?
You already graded the test.
What's that? Yeah, I have.
Can I just see one?
Yeah, sure. I just haven't gotten to Blackboard yet. Finish it now. Okay, there you are right there. You got a real good start. And you can go right next door. Are you waiting on yours? Oh, okay. Oh, okay. I'm sorry. I thought, have you started it? No, you haven't. Okay.
I'll get a head start on it for tomorrow.
Huh?
I'll
Okay.
get a head start on it for tomorrow.
Okay. Do you need graph paper?
Please.
Okay.
Thank you.
You can use formula and equation sheet, scratch paper, calculator. And right next door, I think that brings up. Good job.
Pretty good.
Yeah, very good job.